Okay. Uh-oh. All right, I see you to run. So good morning, everybody. And today I'm going to be we're going to have a discussion of the Lambda CDM Cosmology. I don't think YouTube is running.
Hi, you got to bring the slides up. You got to present and then upload the slides.
Okay. Am I on YouTube?
You're on YouTube, yeah.
I don't see me on YouTube, but anyway. So we should be recording, is that correct?
Yeah. It should be recording.
Oops. Welcome. And
It's still uploading.
All right. Welcome to CMPS discussion of CDM cosmology. And the plan here is, excuse me?
Carry on.
All right. I think YouTube has started. All right. Well, okay. And are we good to go? Running correctly? I'm not getting any feedback. All right. Lambda CDM cosmology of what this Lambda CDM cosmology is. And I'm going to present some slides and then I'm going to pause and I'm going to bring up people and you can make comments. So you should be on the stage. Whoops. Well, I'm not sure what's going on here now. Oh, here we go. Okay, we got Roger, Vladimir, and Dennis. Okay. Anybody else that I see in the green room? Oh, there's Jerry and Nick. Okay. All right. So you see the presentation here on the screen. I have to do full screen. Is that correct?
Yes.
So everybody see the presentation. You can talk and let me know. Give me some feedback.
Yes. We can see it, but it should be larger.
From StreamYard. Okay, so is it working, guys?
Should be larger.
Okay, give me a go ahead. Let me know. Give me some feedback. All right, you see the presentation here?
Yes.
think I'm on the right. Oh, this is the, no, this is the wrong. All right, Lambda CDM Cosmology, right? Does everybody see that? All right, good to go. All right, what is this Lambda CDM Cosmology thing? That's what they call the Standard Cosmological Model. Sabine Hassenfelder calls it the concordance model, which I think means that most cosmologists or physicist experts are agreeing with this model. And I discovered that this terminology is not particularly recent, that it's been used for a while. Okay, so what is, and most of this comes out of Wikipedia. So most of these comments can be found in Wikipedia. If you want more detail, go to Wikipedia. Okay, so in the Lambda CDM cosmology, we start off with the Big Bang. So we have basically the Big Bang cosmology, which is in the old days was the standard cosmological model that was accepted as valid. And then due to observations, we discovered that a cosmological constant needed to be added. So they added a cosmological constant because the standard model that was then existing didn't really comply with the observations. The other thing that is added to this model is the postulate of cold dark matter denoted by CDM. So you get Lambda CDM cosmology because Lambda stands for the cosmological constant and CDM stands for cold dark matter. Now in the universe, the ordinary matter coexists with CDM, cold dark matter, but the cold dark matter is basically unobservable and is only detectable from its gravitational effects and on matter. So in other words, rotation curves in galaxies. So it has a gravitational effect, which is detected by observing the motions of luminous matter, stars and galaxies. It doesn't affect EM radiation according to the standard interpretation. Okay. This model basically assumes general relativity, and that involves an expansion of metric space. And they claim that's well documented both as the redshift of the spectral lines that are measured in galaxies and quasars. And they also claim that there's time dilation in the supernova luminosity curves. Now, here's one of my comments here. What is meant by metric space is not really made clear. So you have to kind of understand what they're talking about when they use the term metric space. And to me, metric space is just an empty void, nothing. So it's not really anything. It's just an abstraction. So we have to have another assumption that we have in here, which is there is a direction to time. Time is moving in a particular direction, and that there is a universal time scale. Okay. And then the cosmological principle applies. And I'm going to go into that a little bit later. This is where, when you start talking about the cosmological principle, there's different meanings that can be attached to that. So do we have any questions so far? Any comments, questions?
Not for me. Comment. No.
Well, as far, hello?
Okay, so go ahead.
Well, I thought that Vladimir
Go
had,
ahead.
in one of Vladimir's presentations, he had mentioned that the dark matter shows up with other electromagnetic waves, which this says it doesn't. So I was unsure about that, because that sort of had me not really convinced, but giving it some credence that I hadn't before. But then I heard people sort of shouting it down at some level. So I'm unsure what to think.
Okay.
Let's continue. We will
think
talk
what
about in
They're
discussion.
saying
guys.
here, I think you're talking about the definition of cold dark matter. It doesn't, if it react with, if you could detect it with light, then it would be detectable, right? And so the idea is that it doesn't respond to EM radiation or light, and that makes it undetectable. So this is kind of the conundrum of dark matter, which is that it's inferred to exist by gravitational interactions, but it can't be directly detected. Does that make sense to you?
Yeah.
Let's continue, guys.
Okay. And this is where it gets a little, I'm not really clear about exactly how the dark energy aspect enters into the equations that they're using. And I think that's an area that we need to look into, or something that needs to be understood a little better. But this lambda, the letter lambda, represents the cosmological constant, which is associated with the vacuum energy or dark energy in empty space that is used to explain the acceleration or in the expansion of space. So space is supposed to be accelerating in its expansion. So in my view, you have a couple of issues here as to what is expanding and why is it increasing its rate of expansion. And okay, so I'm going to go and mention here that Lemaitre was the first one to really basically solve equations with this lambda, other than Einstein, which had a static universe. So Lemaitre, the Belgian, who's a priest, was one of the first to basically examine solutions of general relativity with the cosmological constant included. And one of the ironies of it is, many years ago when I was in college and afterwards studying astronomy, they said that the cosmological constant was Einstein's mistake. Now they brought it back. So it's no longer Einstein's mistake. Okay.
It's a remarkably different theory, though.
Well, maybe you could say that. That's an issue that we might want to consider. According to the experts, that I have a little drawing here that says 74% of the energy in the universe is composed of dark energy. Now that's quite a lot. Dark matter is 22%, and then actual stars, etc., according to this chart, is very small, only 0.4%. You also have interstellar matter and intergalactic matter, and hydrogen gas, neutral hydrogen gas in between galaxies, and that sort of thing. Now, that supposedly, I guess, makes up 3.3%. So this dark energy is pretty big, and the dark matter is also pretty big. So we have the two biggest components of the universe are things that we don't know what they are. That's kind of interesting. Okay, here's the Lemaitre model. Okay. Oops, slide 6. Okay, so the Lemaitre model, you'll notice that there's time is on the bottom, universal time. And so the universe expands, and then it gets to a stagnation phase that is called in this diagram. And then it starts expanding again. So the rate of expansion accelerates. So it initially expands, then stagnates, and then starts expanding again. All right. I think I went backwards. Okay, so here's the NASA drawing of the CDM model. And this is sort of a three-dimensional representation. So we have the quote, what I like to call big flash at the origin. We see that's on the left. Time is expanding to the right. And we see that there is a kind of what they call the inflation phase. So there's a rapid expansion of the universe during the Big Bang and the expansion phase. And then there's this, it's not really expanding very rapidly after that. And they call that development of galaxies, planets, etc., the phase in the middle. And then as time goes on, it's flaring out. The acceleration is supposed to be accelerating. So that's what they're saying that dark energy is. This is another diagram of it. This may be a little clearer. You see on the left-hand side, then this rapid expansion called inflation, and then there's a slow expansion, and then expansion is accelerating. And so that's essentially the current thinking about this. So we have any questions about these diagrams? Okay.
Well, Harry.
I like the term big flash. Yes, go ahead.
Harry, did they explain why there was, let's see, did they explain why there was a start of a stagnation period and then later on a start of an acceleration of expansion period?
That's a good question. I don't have an answer to it. I think it has to do with the way the model parameters are put into the model. So if we go back to the Lemaitre model here, this stagnation phase that is in this model, the Lemaitre model, as I understand it, is not supposed to last for very long, a couple of million years maybe. But when you get to the NASA model, the NASA drawing, it looks like this stagnation phase takes quite a long time, and it's billions and billions of years, and only the acceleration is very weak. So it's not, doesn't to me look from these diagrams that the acceleration is increasing very rapidly until later, after galaxies have formed and started evolving. Does that answer your question?
Yes, but I'll make a postcard. The reason why I asked that question is, as I understand it, there was a problem with the Big Bang theory and the inflation period, which is, an incredibly fast expansion of the universe in an incredibly short period of time, was a ad hoc fix. There was no experimental evidence for it, and I've never seen a claim as to why it began, or the physics of why it began, or the physics of why it started. So so I was suspicious about.
You missed it. Yeah, that's okay. So that seems to be one of the areas in which.
Harry,
Okay, let me respond to what Nick said. All right, go ahead.
My question is very simple. Cold dark matter and dark energy, where they came from? what is the origination with some process, something, where they came from?
Well, I think
Well-
they're named dark because I don't think the current cosmological community has any understanding of what they are or where they came from.
Where they came from, this is my main point. You know, in a Big Bang model, there is no dark matter, dark energy, and it's what is important, 74%, 22%, so huge, and no explanation where they came from.
Okay. I think the answer is that the current, the standard Big Bang cosmology, okay, Weinberg, I have Weinberg's book. He's got a textbook, Gravitation and Cosmology, Stephen Weinberg. I had this book for a long time, and he talks about the standard cosmology. This is 1972, so they think they've established in 1972 what the cosmology is, what the correct theory is, and then the observers who are doing measurements find out that, well, their predictions don't exactly match the observations, so they have to come up with some kind of ad hoc fixes, and looks like dark energy and dark matter are ad hoc fixes. Does that answer your question?
Yes, it's ad hoc. I like this explanation.
It's
Okay.
they're both fudge factors, and I would say they're dark fudge factors. Much as I like to eat dark fudge, I don't think it has a place in physics.
You know,
Well-
in early paper, I'm sorry. In
I'm not
early
really
paper-
sure. I'm not really sure why they came up with the term dark energy. And it turns out that there's other terms. There's quintessence, and which apparently means the same thing. And
Actually, with dark energy, Einstein's original cosmological constant, what he explained it as an anti-gravity, where when galaxies or objects get really far apart, that instead of attracting, they repel, like sort of an anti-gravity. So it seems that dark energy is rather a force instead of a mass. Like gravity is a force. We don't say that gravity, we don't say gravity like takes up whatever percentage of the universe. So why would they say that about dark matter? It seems more of a force instead of a mass.
well, okay. So to answer that question, I'm glad you brought that up. The primary assumption of the physics community is that general relativity is correct.
Yes.
And that any theory or that they propose has to agree with general relativity, which is Einstein's theory. And general relativity doesn't have a gravitational force in it. So there's no force.
Well, you can sort of play around with the word force. I mean, many see gravity as a force, and many explain it other ways. However, though, whatever gravity is, they don't consider it. Well, it takes up like whatever percentage of the universe, the way they said that dark energy does.
Well, I think that's a good. Okay, you're getting into the weeds here of where these numbers and claims came from, which is certainly something that needs to be investigated. And I don't disagree with that. I do know that I went online and looked at a course of general relativity. There's lots of YouTube videos and go into lots of details about this. And I didn't really get any satisfactory answers to any of these questions that you're asking. I can only give you what the answer, the canonical answer, the approved answer that they give, which is gravity is not a force.
Yeah.
Okay. That's the standard answer to the when you use the term force and gravity, then you're not talking general relativity. You're talking something that's outside.
It might depend on how you define force. I mean, something's clearly going on where something that appears to be a force is occurring, even if it's explained some other way. But my main point about dark energy was that it seems a force or something other than mass, at least. Anyway.
Well,
That's okay.
I think that's the reason why they're using the cosmological constant, is that that's the closest thing they can come up with that explains the observations. But what the cosmological constant is a term in an equation. So there's a term in the equations of general relativity that's this cosmological constant. And so they've inserted that, and that basically is a parameter that's supposed to represent dark energy.
Yes. Before the Big Bang, of course, general relativity was the universe that Einstein conceived of and its cosmological considerations was vastly different from the Big Bang. I mean, just completely different. There isn't any real evidence for the expansion of the universe or the Big Bang, I don't think.
Well, you're sort of jumping ahead of the conversation.
Let's go, guys. Let's continue. And we will talk about all these issues after you will finish your presentation. Harry, please continue.
Okay,
No slide button. Hello.
Go ahead.
Yeah, so on this issue of saying gravity is not a force, that is what some of them say, but it turns out to be arguable because some of them will say it is a force. So you've got the contradictions again. Some will say one thing and some will say something else. And from one point of view, it's supposed to be that Newton talks about it as a force, and Einstein talks about it as space-time curvature, but it's the same thing, just talked about it in different languages.
Well, yes. And that's one of the difficulties that we have is trying to understand what physicists are talking about and interpreting what they're saying.
They contradict themselves.
Right. And part of the reason why I'm making this presentation and talking about this is so we can understand a little bit about what the language is being used and what it means. Otherwise, it's just incomprehensible words that you don't really understand. So how can you understand it if you don't understand what the meanings are that are being attached to it? So that's one of the things.
People use different meanings to the words.
Right. And we're going to find that out here.
Okay.
Okay. So
it's arguable. Or it ends up arguable.
No question about that. Okay. I'm going to talk a little bit about the big flash. I like the word big flash. This word Big Bang. You'll notice that Wikipedia, I took this from Wikipedia, they have it in quotes because, which was not an explosion, but an abrupt appearance of expanding space-time containing radiation at temperatures of around 10 to the 15,000 Kelvin. Okay. And this was followed by the exponential expansion. So there's inflation in the accepted standard model. So that's inflation, and expanded by 10 to the 27 times. These are big numbers, and it's happening in a very small increment of time, according to the essentially the way they're talking about it. And of course, this big flash was supposed to happen where the particles, as I understand it, are primarily electrons, and it's opaque. So it's opaque, and so it's a bright ball of flame, if you will, a big flash, and it occurs very quickly, and then the cosmic microwave background radiation is produced, and then it starts cooling off, and then they have what's called the recombination phase, where the microwave background radiation decouples from the material that's very hot, and supposedly the result is this black body radiation that's produced called the cosmic microwave background. Okay, here's another drawing. I like these pictures. I think they're kind of interesting. In this one, we see that the expansion seems to be exaggerated. And I'm not sure that it's this, that the dark energy expansion that's supposed to occur in the later part is as great as this. But this sort of shows, so the idea is you have a big flash at the bottom, and it's microseconds or very, very fast. You got this big fat flash. You have all these elementary particles, a soup of particles, and this is supposed to be what they call optically opaque, so that it looks like a black body. And so you get black body radiation, and then it expands. Okay, then you get what they call the dark age. I didn't know what this meant when I first saw this term. That means that the flash is over, I think. Okay. And then as time goes on, supposedly galaxies are created out of the matter of the Big Bang, which turns out to be supposedly hydrogen and helium and lithium. And then this is one of the problems. The amount of lithium is a problem. Okay, now I'm going to talk a little bit about dark matter. So does anybody have any questions about the Big Bang phase? No questions. Okay.
Well, I just entirely disagree with the Big Bang, but I'm unsure of everyone else's view here, or if this is just being presented.
Well, there's a lot that goes on there that it would seem to me requires esoteric knowledge in physics. I've read Steven Weinberg's book, The First 3 Minutes, many years ago, and I don't really think I understood exactly what he was talking about. And there isn't really understanding to it, though. I mean, there's no way that time and space couldn't exist, I don't think, before the pinpoint exploded. How did the pinpoint get there? What caused it to explode? Well, you're asking too many questions.
Yes. Let's continue.
When I get further on down through here, I'll get into the philosophical aspect of it, and we can talk about that a little bit more. So now we're at the dark matter thing. Okay. So you got dark energy, which is kind of, its effects are shown or detected by observations. And these are observations that are very difficult, and they could be controversial, supposedly based on supernova type 1A measurements using, I believe, the Hubble telescope. So, and I think it was the Hubble telescope that supposedly produced the results that allowed this Lambda CDM idea to the dark energy idea to be introduced. Now, dark matter is a bit different in that dark matter comes from Zwicky, Fritz Zwicky, and he's usually attributed to. And then what Zwicky did was he was looking at galaxy clusters, and they have this mathematical principle called the virial theorem, which supposedly galaxies are gravitationally bound, and you can estimate the amount of mass in a galaxy cluster. They're moving around in orbits, okay, and supposedly gravitationally bound. And you can calculate the energy by this virial theorem. And what he found was there wasn't enough mass there to explain the velocities of the galaxy. So there was a discrepancy. And this discrepancy was removed by the hypothesis that there's dark matter there. So this is, I think where this whole business of dark, the use of the term dark comes from, I think it comes from Zwicky, and but that's just my guess about where the terminology came from. During the 70s and 80s, when I was studying this sort of thing, it was called the missing mass problem. Okay, when they did these measurements, they did measurements and they didn't have there wasn't enough mass, and that they, based on the brightness of stars that they were measuring, there wasn't enough mass to account for the velocities. And so there was well, we can explain this if we say there's some kind of missing mass. But the missing mass became dark matter. And I'm not really sure exactly how that terminology came about, but it sounds, I guess it sounds better, because it sounds mysterious or something. I'm not sure why science would do that. Okay. So
Harry,
yes.
I thought it was dark matter came from the observations of a spiral galaxy, not galaxy clusters.
Now, what I mentioned was Zwicky was the one who originally did the galaxy cluster work. Later, Vera Rubin they determined the rotation curves were moving too fast, and they needed missing mass or additional mass to go in there. So there are actually two aspects of it. One is the virial theorem in galaxy clusters, and then there was the Vera Rubin. She wasn't the only one, I don't think, but the rotation curve problem, that the rotation curves don't come out right. So basically, in both of these cases, what you have is the gravitational theory doesn't match the observations. So
right. Well, the problem is that they weren't using the correct math to calculate the rotational speed. If you use the correct gravitational force, then well, I shouldn't use force. Correct equations, then you don't need it.
That's another question.
All right.
You have a couple of theories. You have MOND, M-O-N-D. You have MOG, which is another one. And then there's something called ALAND or AQuant, I think, that are essentially, and I looked into this a little bit. What they're saying is, in physics, everything has to agree with general relativity. General relativity is right. So the assumption that they're making is we're not going to change general relativity and the laws of gravity. We're going to postulate something to exist that we can't see or measure directly, but it fixes our theory. So it's an ad hoc postulate.
Right.
Okay. So, okay. So that when they talk about cold dark matter, and this comes out of Wikipedia, it's non-baryonic, consists of matter other than protons and neutrons and electrons. And then it's cold. So dark matter is cold, so it doesn't produce any radiation that could be detected, has not very much velocity, so doesn't have a temperature. Okay, it's not moving fast, so it's cold, doesn't have a temperature. Isn't affected by radiation. It doesn't radiate anything. Okay, so what we have here is criteria for dark matter, which means that it can't be its existence can't be detected and it can't be falsified. So there's no detection of dark matter particles. Does not interact with the electromagnetic force. It doesn't absorb, reflect, or emit light, making it extremely hard to spot. In fact, researchers have been able to infer the existence of dark matter only from the gravitational effect it seems to have on visible matter. Okay. So this is the classic ad hoc hypothesis that's not falsifiable, it would seem to me. Oops. Okay, so I went at the CERN website. They say many theories say, go ahead.
Oh, I'm sorry. If it is thought that dark matter sort of consumes so much of the universe, if it's so all-encompassing, why would it? I don't understand why it would account for the unexplained gravitational effects if it's so ever present. I mean, it was if it was in a certain place, it would seem that the gravity, things would gravitate towards that. But if it's everywhere, I don't understand. I don't get it.
Well, I don't know how. I'm not sure I can answer that. I think of dark matter as being the ether that they banished. So if dark matter was ether, it would make more sense to me. But I don't think
I thought that ether was sort of more uniformly across the universe, where there's ether present everywhere, whereas dark matter only takes up 70-something% or something.
Well, it's not clear that it's uniformly distributed. It has to be concentrated in galaxies in order to explain the discrepancy that the gravitational theory doesn't work as it's supposed to.
Yes.
And in clusters of galaxies. So you think of dark matter as something that's like a halo around galaxies and a kind of halo that surrounds galaxy clusters, and it's denser around bigger galaxies and less dense around smaller galaxies. Does that make sense to you?
Yeah.
But I think to me, dark matter sounds like they're talking about ether. Okay, so essentially what I want, CERN says, well, we haven't, they're not detected. They can't detect it at the LHC, but it should be. We'd get some discrepancy. No, they haven't found any discrepancies. And there's been a lot of experiments. Sabine Hassenfelder has a good video where she talks about this. And Veritasium has a video on YouTube where he gives a list of all the experiments that have been done. And supposedly, according to him, only one experiment in Italy detected anything at all. And many years ago, I went to Jefferson Laboratory. They call it JLab, which is located here in Newport News. And they had an open house. Every couple of years, they have an open house. And one of the displays that they had set up was their dark matter experiment. And, they didn't detect anything. So this was very popular for about 20 years, looking for dark matter. But nobody's really been able to find it.
So it is thought, or at least it was thought with this hypothesis, that dark matter exists all around our atmosphere of Earth, for instance. I mean, like in addition to the universe.
Well, I'm not sure. I think of it as an ether. So as far as I can see, it's just another word for ether, but it's not a uniformly distributed ether. It's an ether that is, like, say, for instance, concentrated around galaxies like a halo, an ether halo. So maybe there's an ether halo around the Earth, and each massive body has this dark matter ether halo around it. But that's just my thinking about it.
Yeah, but then Jerry's point would still be valid because it may not be universally symmetric, but around the Earth it should be equally distributed.
Well,
symmetrically distributed, so the pull from one side would.
We're basically speculating about something that's a non-falsifiable ad hoc hypothesis.
No, I was just rebutting what you were saying about that, rebutting
I'm just
Jerry.
saying, I think of it, to me, I don't understand, I don't see the difference between dark matter and ether.
Well, many etherists would totally disagree. I've heard several different interpretations of the ether. That Spixie's stationary, that it's flowing around, that it's a gravitational field, that it's electric. That's a few.
Well, that's to me, ether is an ad hoc hypothesis. So it seems to me you've got dark matter as an ad hoc hypothesis too, and ether is supposed to exist to carry electromagnetic waves, and dark matter is supposed to exist to explain the divergence in the gravitational anomalies.
Yeah, I think Michael Morley's original idea was simply that the ether propagated light, but it's grown to people think that it propagates everything, like objects, like literally everything in the universe, that it causes reality somehow.
Well, I just brought that up because it just seemed to me like dark matter is an ad hoc hypothesis like ether is, and it reminds me of where the idea came from, which is this universal quintessence. Aristotle talks about the quintessence, which means that it's the substance of the ethereal heavens. Okay, and so then the word ether comes out of that. So it seems to me that dark matter is supposed to be the way they were thinking about it, but they never detected it. It was supposed to be some kind of particles that are hidden, that act gravitationally, but you can't really detect with, you can't see them, you can't, they don't really interact in any way other than gravitationally. So they're hidden, i.e. dark matter.
And we don't know what they're composed of. I mean, I doubt they're composed of subatomic particles, for instance.
Well, I think a lot of these experiments that I referred to, and again, we're just trying to understand what these concepts are, what these words mean. They've done all these experiments, and like, for instance, the one I mentioned at JLab, JLab is a particle accelerator laboratory. So they're looking for some kind of particle that would be this dark matter particle. The CERN that I mentioned before, they are looking for some kind of particle, unknown particle, okay, that could be identified as the dark matter particle. And now I think the current thinking is that there's no place in the standard model of particle physics that a dark matter particle can fit. And so dark matter isn't a unknown elementary particle that physics hasn't detected. So I think they've kind of closed the door on that, but I guess maybe the jury is still out. Okay. Now to move on a little bit here. If you go to Wikipedia, they talk about the six parameters. So this model that they're talking about, the ADCM model, the Standard Cosmological model, has these parameters that have to be adjusted. Okay. And these are the six. Yeah. Okay. And so it's sort of like the standard model of particle physics, where you put in these parameters and sort of figure out what parameters make the model work. And I think this is the same kind of idea. You have to fine tune the six parameters. And in my view, you've got all these possibilities of combination of six parameters. So to me, that looks like an infinite number, or practically infinite number of possibilities to test. Okay, now I want to talk a little bit. Does anybody have any comments about that? Okay. Big Bang flaws. Okay, so because this is a cosmology that adopts the Big Bang thesis, we have the baryon asymmetry. There's the discussion of matter versus antimatter. Where is the antimatter? Okay, and Big Bang is supposed to produce antimatter, but there isn't any antimatter according to the observers who have searched for it. So this leads to the question of why is there only matter and not antimatter in the universe when, according to particle physicists, when they do these interactions in accelerators, they can produce antimatter particles, but the Big Bang doesn't produce any, but the actual universe doesn't have any of these antimatter particles as a normal course in the universe. So it's not a common constituent in the universe. So so that's a problem, and it's not been detected outside of particle accelerator. Then there's the magnetic monopole issue. Now, to go to your question earlier, Nick, that you brought up about the inflation, I think the inflation theory was an attempt to essentially remove the antimatter asymmetry problem and the magnetic monopole problem. And it's not real clear to me whether this is completely solved or not. But down here at the bottom, we get to what I think is the most decisive issue, which is the amount of lithium that is supposed to have been produced is not correct. So, initially, when the Big Bang model was thought up, they had this idea that all of the elements were going to be created in this one big flash, this one big moment of creation, and all the elements would be created. But then when they did more calculations, they discovered that's not quite going to be the case. And the only thing they could produce was hydrogen, helium, and lithium. And then the rest of the elements had to be built up in the stars. And then they discovered they couldn't build up enough elements. Not all of them could be built up in the stars. Then they had to basically have supernova explosions. So this, to me, this is really where the real difficulty is with this the current cosmological thinking. Okay, any comments or questions about that? Okay. Now, previously, I talked a little bit about, the general relativity really relies on the cosmological principle and this, what they call the homogeneity principle, which is the universe is roughly the same everywhere. Okay. Now, one of the problems with the current cosmology is people keep pointing out things that don't really, they falsify the cosmological principle. So a lot of people produce papers saying the cosmological principle is falsified. And so we have the evidence from galaxy clusters. Basically, galaxies are clumped together into clusters, and clusters are clumped together into clusters of clusters. And this doesn't really fit the idea of a smooth distribution of matter, which is the basic assumption of general relativity in calculating these models. The general relativity treats matter, galaxies, as if it's kind of a fluid type thing. So there has to be this uniform distribution of the fluid. Okay. So then we have that there's these discrepancies in the cosmic microwave background radiation. I'm not going to go into this. I'm not much of an expert on the asymmetries and the microwave background. There's this dipole effect, which I'm not really that familiar with, but if anybody wants to talk about that, we can certainly do that. Here's the CMB dipole, and so there's some problems with, does the universe actually look like what the assumptions require that it looks like? And there's some more large-scale structures. Now, this is kind of interesting. There are these big, huge structural features that have been detected, and they're too big to comply with the assumptions of the cosmological principle, homogeneity of the universe, that is needed in order to make general relativity valid. At least that's the claim in the argument. A lot of these, Sabine Hassenfelder has a good video where she talks about these. Not much detail, but there's a whole bunch of them, a large number of them. And then, of course, you have other people who say, well, this doesn't really violate the cosmological principle, so there's no problem, everything's fine. There's some more of them: Giant Arc, Hercules, Corona Borealis, Great Wall. So essentially, if you believe in general relativity and the Big Bang, you'd think, this was my idea originally, you'd think, oh, all you'd get in the universe is just a uniform distribution of stars as far as you want to go. I mean, it's just stars everywhere. There'd be I don't understand why you need a galaxy. Why would you need the stars to concentrate to form a galaxy? And why do these galaxies form clusters? It seems to me that if you believe in the Big Bang, all you get out of it is just a uniform distribution of stars throughout space. And that's not what we see. Anyway, that's my point there. All right, we also have these voids. Supposedly, and I was kind of surprised, I didn't really know about this, but supposedly our galaxy, the Milky Way, is in a void, because there are not other galaxies really close to us other than, I guess, the Andromeda galaxy. So we're supposed to be in a void, but there's these other voids out there, okay, which are supposed to be just portions of the universe where there's no galaxies. There's nothing there, okay? And this doesn't really agree with this uniform distribution of matter, which is required by the cosmological constant, which goes into being an assumption of general relativity, which is the fundamental theoretical tool that's being used by physics. Okay, there's the Hubble tension problem, which that the the value of the Hubble constant derived from the CMB experiments doesn't agree with the value of the Hubble constant based on distance measurements, traditional distance measurements of galaxies, where you have what's called the cosmic distance ladder, where they painstakingly measure the distance to nearby galaxies, and then they extrapolate the distance measures out to further galaxies. And basically, the Hubble telescope allowed them to narrow down the error bars in the measurements. And it turns out these error bars in, like, for instance, Cepheid variables are very wide. But the error bars in the measurement of the CMB are pretty narrow. So what happens is as the optical measurements using telescopes, they manage to narrow down the value of the Hubble constant using those measurements. The distribution of errors for the CMB and the optical measurements, they don't overlap. So that's called the Hubble tension because the error bars are separated. You have any questions about what I was trying to explain there? It would be better if I had a diagram, but I don't. Then there's the axis of evil problem. I think that's been talked a lot about. I know. Then there's strong equivalence principle violated in observations. And I looked into this and I really got confused as to what they were talking about. The strong equivalence principle is, I believe, that acceleration is equivalent to gravity. So the gravitational force, I hate to use that word, gravitational force, is equivalent to acceleration. And I think that's the strong equivalence principle. But when I started looking at this, I got kind of confused. But the point being that the strong equivalence principle, or the equivalence principle, is really at the foundation of general relativity. So if you could find a violation in that, that would basically knock general relativity over. Now here's another problem with the CDM cosmology, is that it predicts too many dwarf galaxies. Okay, and then data from the Planck mission shows hemispheric violet. Okay, so we got a asymmetry. This might violate the isotropy rule. If you have a hemispheric that says the universe looking in one direction is not the same as the universe looking in the other direction, and that kind of violates the assumptions. Okay, any questions so far before I get into the philosophical criticism? Okay, and this is mentioned in Wikipedia, that the Lambda CDM model is non-falsifiable ad hoc. We talked about the ad hoc aspect of it. So that's kind of unacceptable if you just basically have a lot of these ad hoc assumptions that just keep getting added on. And particularly in the case of dark energy and dark matter, we don't know what these things are. Okay, so then the other one is that it's scientific conventionalism. Now, I didn't really understand what this meant until I started looking up. But essentially what conventionalism is, some people refer, and I've talked about this before in other, that Einstein's theory is correct because they say it's correct. And if you try to say it's not correct, they don't listen to you. And that's kind of an example of what conventionalism is. It's society, people have gotten together and decided this is what's correct. And, because everybody is supposed to believe that this is correct. And if you don't believe it, you're not marching along with us.
Well, I would say that goes for all of mainstream. Sorry to interrupt you.
Well, we've talked about this before, but the main point I'm bringing this up is because there's a name for it. So now we have a name for it, and it's not unusual. I think you'll find it in politics and a lot of social science, society-oriented things. The point about science is supposed to kind of be beyond social pressures. It's supposed to be able to access truth. That's not, you're supposed to be able to trust it. And anyway, a good example of what I think is a good example of this idea is when they talk about climate change, they say 97% of scientists agree that climate change is correct. That's an example, I think, of scientific conventionalism. So the argument becomes your disagreement is invalid because 97% of all scientists disagree with what you said.
By the way,
So then,
I don't want to shift to climate change, but that's the claim. The claim is supposed to put a lot of pressure on all those who disagree, but nowhere
Right,
near
and
97% agree with it.
Right. I think that's an example of what is meant by scientific conventionalism.
Yeah.
It's that it's an attempt, and everybody has to. I mentioned this a little bit earlier, which is I saw a video by this guy Moffat who came up with this Moog theory, and he was trying to explain how he came up with this theory. And the first thing he says is any theory has to agree with Einstein's general theory of relativity. Okay, and so you're trying to come up with a theory that explains observations that disagrees with the accepted theory of gravity, but your first postulate is it has to agree with the accepted theory of gravity. And so I immediately think to myself, well, you're not going to accomplish anything if that's your starting point, that it has to agree with Einstein. All right. And this came up early, lingering unresolved issues. Jerry mentioned this. Does redshift imply universal expansion? I think people are still arguing about that. They're skeptics. I'm kind of skeptical. Untested alternatives to the explanation of the CMBR. I just don't understand this CMBR, their explanation of it. The black body radiation, there existed at some time in the past a black body, this opaque, this is like a billionth of a second after the initiation of the big flash, and you had this black body radiation, and then the universe cooled, and this microwave perfect black body radiation was created, and that's what we see, and that's proof. But a lot of stuff happened after that, but it has no effect on the CMBR, but we don't see that when we measure the CMBR. So I just don't understand what any of this is. Okay, we talked about this. What is dark matter? Experiments can't detect it. Then there's the question, what is dark energy? Now, I did a little, there's also this idea of quintessence. I'd heard about quintessence, but I hadn't, I thought I don't have a clue what that is. That's another idea of dark energy. There's something called holographic dark energy. And so there's a couple of, there's some different concepts that are related to this dark energy idea. I don't think these are a lot of adherence to these alternatives. Then there's this issue of metal abundances. This gets back to what I think is really the main problem, is that galaxies at very high redshift don't have high metal abundances in them, but they're not supposed to, because there's not enough time for stars and galaxies to evolve to have created the heavy elements. And yet, when they're looking at these high redshift galaxies, they see high metal abundances, and so the abundances don't match up. Okay, I borrowed this. I saw a presentation by this guy, Martin Lopez. He says, there is not a full consensus that the standard model of cosmology is well established and with clear interpretations of all the observations. So I think maybe that summarizes kind of my opinion, and maybe the opinion of other people here. And so I thought that was a kind of a well put conclusion. And since I borrowed it from somebody who was a professional astronomer, I guess that kind of justifies putting it in this presentation. So that's the end of what I have to say.
Okay. A few points. As I understand it, the cosmological constant was not a necessary output from general relativity. Einstein created general relativity, And then he saw certain problems, and he created out of thin air the cosmological constant. And
Not sure why.
And it's I've forgotten why. I used to know why. But it's changed over time as to what it is. I mean, it's first it was the savior of general relativity, and then it was wrong, and then it was meant to be consistent with expansion. But I'm saying that was an ad hoc addition. It wasn't directly derived from the field equations or anything like that.
I would say that a lot of ad hoc ideas are just simply trying to put band-aids on
Nick.
a theory that.
Nick.
Yes. Yes? Harry, were you saying Nick?
Well, as far as why the cosmological constant was originally conceived.
Nick, you're breaking up a little bit.
That's Jerry.
Okay,
Yeah, you're breaking up.
I can hear Jerry.
Hello? I think the original purpose of the cosmological constant was because Einstein thought the universe would seem unstable and that everything would collapse into
right.
Yes, go ahead.
Simple point because of the gravity. So he invented the idea that there's an anti-gravity that pushes galaxies apart.
Right.
At least that's what I remember.
Yes, yes. Thanks for the reminder. So it came in kind of as a, ad hoc fudge factor. And then it was dismissed, and then it became useful when they thought there was the universe was expanding. Another point, let me just emphasize that right now, the Big Bang Theory has in it that short period of inflation where the size of the universe increases by a factor of something like 10 to the 37th in the time of 10 to the minus 29th of a second. That, to me, is unacceptable. And there's no explanation to why it started or why it ended. So that clearly is a fudge factor to save theory.
There really isn't any good explanation why the universe is expanding at all. I don't think.
Just one other point, Harry. I think on your equating dark energy to the ether, that's a perfectly legitimate point of speculation, and I did that all the time. But I think it tends to just confuse two different sort of vaguely defined concepts. Maybe it's better really to try and keep them separate. I mean, you can explore it personally as deeply as you want. I don't think it's inherently contradictory, but I don't see the connection at the moment. I see them as two different, possibly overlapping a little bit, constructs. And as a final thought, I was mentioned, according to Newton, we have force equals mass times acceleration, and now it's acceleration, except when mass is accelerating by gravity, suddenly it's not a force. So those are the points that I wrote down.
Well, I bet Vladimir has something to say.
It's so much to say. I've done 8 presentations to show that Big Bang model doesn't work. I cannot repeat all these 8 sessions, at once. But let me tell you, first of all, dark matter, even in the first pages of its wiki, was invisible matter. Dark matter nobody understands correct. Invisible means that they cannot see in visible spectrum of our eyes. That's it. That's the first question. The next question, gravitation, it is classical physics. And classical physics, it should be macro objects. There should be some ensembles of particles. That's why when they're talking about gravitational forces between particles, dark matter particles, it's absolutely wrong. Because, first of all, there is no gravitational forces between our standard particles, electrons, protons, neutrons, and so on and so on. Nobody never talked about the gravitational forces between them. Why we started to talk about the gravitational force between dark matter particles? They don't have gravitational force. Gravitational force, it doesn't matter how we name it. It's a classical effect, and it's only bodies. It should be some invisible bodies. And Zwicky, he saw invisible body means center of these supercluster. Who told that it's a dark matter, invisible matter? He told that's it, because he had only a standard telescope. The next very important point, let me remind you that Mitchell in London, 200 years, I don't remember how many years ago, named already dark galaxies. He even talked about dark stars. He talked about how to even observe them, That's why it is not Zwicky who pronounced it's dark matter. Dark galaxies, dark stars existed before him for 100 years, maybe 200 years. I don't know how long. I didn't calculate this time. That's why, there is a mixture. And they're trying to create these dark matter particles in accelerators. It's not the way it goes. It will not go at all. Homogeneity of the universe, it doesn't work. Any principle of Big Bang model doesn't work at all. There are no observations that they confirm their, belief, even vacuum. Fast radio bursts, we know about them. There is the intergalactic medium, and there is a concentration of it, about 5% of the matter, and it's confirmed, it's approved by experiments. That's why even talking about speed of light in vacuum and all this stuff, there is no meaning. That's why, I'm totally confused with them. And I don't believe that smart guys can, even accept all this, all the stories about the Big Bang model, I'm very sorry, but, it's
Well, I would, I think you make the point. I'm going back to the conventionalism thing, which is,
yes,
yeah, in public, maybe they say, "Oh, yeah, I agree with this," but in private, when you sitting in a bar and he's had a beer or two, you'll say, "Yeah, I think it's all a lot of BS." But he's not going to stand up in front of a group of other physicists and say that. So I think that's a conventionalism thing. They in public, they have to all pretend to agree, but maybe not so much in public. And
you're absolutely right. It's a
so
new religion in physics.
maybe they don't really.
Exactly the point. There is no difference with any other religion. You believe or you don't believe, and that you take it or you didn't, and that's it. If you didn't take it, throw away. Throw away. That's it. You're absolutely right. It's conventionalism, and what is important, they don't believe themselves. They follow this, Big Bang model only to have grants, money, and all this stuff, It's a great pity.
Well,
for
my
me
question
that
is, and
right
I'd
now
like
it's
for
not a
somebody
science.
to give me.
It's a business for people who knows what they're doing for money. Sorry.
I'll just mention to Dennis that
Okay,
his
so here's
mic
my
is
question.
muted.
My question.
Dennis.
Your mic is muted, Dennis.
Okay. My question is,
Unmute.
yeah, he's still muted.
I
Up
find,
now he's unmuted.
can you hear me now?
Yes.
Yes.
I find this
Yeah.
classical cosmology extremely difficult to believe. And I also find it hard to believe that anyone else would, have been trained scientifically to be accurate and so on, they also believe it. It's, it has a religious hint to it because it has a creation. The creation is the Big Bang is what takes the place of creation in theory. And it's combining like this in that manner, religion and science has a very poor record throughout the history. I believe there was a creation, but if Almighty God set the laws of physics, He can also change them. That's what they don't want to accept. So there's all this hocus pocus that they throw in. They know that general relativity can't be correct because the outer planets of the solar system would fly off into space. They wouldn't have good orbits. You couldn't predict their orbits if gravity propagated with velocity c, which is what the general relativity people postulate. So it can't be right. And as I said, it has a religious flavor to it, with the Big Bang being the creation. And I'm very skeptical of it. Very skeptical. And to the point where I can't understand how anyone who has been trained scientifically to be accurate and so on could really go for it. They having postulated that God does not exist or doesn't really affect anything. They've thrown out the baby with the bathwater. So they have to, but they want to include it back in through the back door, so to speak. To me, this cosmology is futile. And I actually feel sorry for anyone who can believe it.
Okay.
So that's my statement. Thank you.
Harry, I think James might want to join, if that's okay.
Well, Harry is working on that. I'll just mention that physics academia's construct of dark matter.
Nick, I'm not really hearing any.
Are others hearing me?
I hear you.
Yes? No?
I can hear you.
I hear you. I'm not hearing you very well. I'm not hearing you very well.
Okay, well, I think others are. Let me see, I have this. The Physics academia's construct of dark matter came from looking at the rotational rate in spiral galaxies. And the problem was that they used their implementation of the equations were an assumption that the mass was spherically distributed. Whereas if you do it correctly, and do a sum of all of the masses in a plane, it comes out to be correct. Correctly predicts what the rotational rate is. So the construct of dark matter that academia holds is based on a false premise. And they tried to search in the solar system for evidence of dark matter, did not find it, based purely on gravitational anomalies. So I'll just make that point, and that's why I've suggested it to Vladimir that he use a different term than dark matter, because it means something totally different to physics academia and cosmologists.
Someone suggests, such as Shockwave in the chat room that I've seen several times, he suggests that the electric universe explains dark matter and many other observations. I don't know what anyone else thinks about that, though. Electricity. Any thoughts? Maybe that's far out there.
Yep, good point.
Maybe we should refresh ourselves as to what this electric universe people are actually saying.
Well, I wouldn't say that I'm that familiar with it.
Well,
I read something
that's a whole different bag of worms. That's a whole different bag of worms. If somebody wants to make a presentation about that, they're perfectly welcome to do so.
Well,
does anybody want to volunteer to do a presentation on what the electric universe theory is?
Well, better would be to invite someone from the electric universe to give their presentation on their thesis.
You're right. It's a good proposal.
I would have the interest.
I'll do it. I'll send out an
I know
invitation.
that Jim Marsden, in one of our discussions, was talking about Eric Lerner's theory. And I went to Eric Lerner's website and I couldn't understand pretty much, it was kind of like all over the place. And so it's kind of, he didn't really have a presentation or anything where he said, this is my theory. It was just a bunch of different blogs that he had put together. So one of the issues that I have in talking about electric universe and this sort of thing is, what are they talking about in an explanation that you can give it to me in 30 minutes? That still sounds to me like a long time to hear about it. I've never really heard what their fundamental argument is. What are their fundamental claims? I've never really understood that. So there needs to be a fundamental explanation about what they mean by electric universe and what the theory involves.
Okay, let me pursue that. I'll pursue trying to set something up. It won't happen in the near term, I don't think.
Well, there's a lot of
I'll talk to Thornhill or someone of his stature.
So Nick, here's my proposition. Okay, this is kind of what I get out of talking about this, and putting together this presentation. Looks to me like general relativity doesn't match the observations. So at what point does the mainstream accept the fact that their general relativity theory isn't really working and it's time to look for something else?
Okay, let me make a point that I've alluded to in the past. To me, there's a dichotomy between Einstein's gravitational field equations and the rest of general relativity. Now, Einstein's gravitational field equations predict what they call time dilation. It's really clock retardation as a function of the difference in gravitational potential in two different locations. And GPS data is consistent with that. But when they were broadening general relativity to beyond just gravity, they added in a lot of problems with special relativity, like the constancy of light, speed of light, and also the equivalence principle, where the data from general relativity says the equivalence principle is incorrect. So I just think, keep that one thing in mind, the difference between the original gravitational field equations and the rest of special relativity. I don't want to throw the baby out with the bathwater, but and by the way, I don't agree with the curved space-time interpretation or even space-time construct of general relativity.
With gravity causing time dilation, David DeHilstra has suggested many times, or more than suggested, basically, that people who work with GPS know that it isn't true, but they don't want the controversy. They don't want to step up and say.
No, Ron Hatch, who was the expert on data, was very strong that the data disproves the equivalence principle and proves the dependence of clock rate on the difference between gravitational potential in two different locations.
So we're back to my question, which is how long is it going to take for this physics establishment to realize that their gravitation theory, general relativity, isn't correct?
Well,
to steal a phrase from the stock market, it's going to be when there is sufficient fear of missing out, FOMO.
Maybe many of them aren't introduced to alternate ideas.
Well, in FOMO, there has to be
an
approach that works better, and eventually people have a fear of missing out if they don't participate in that new approach.
Well, I also think there's another factor, and that's the fear of loss of prestige and the change of their ego. A tremendous blow to their ego.
Well, if any of them suddenly change their mind,
as I said, conventionalism is operative here. So remember that.
Yes.
So in science, the rule is supposed to be if the theory doesn't match the observations, the theory's wrong. I think you see a lot where people said Feynman said that. And but it looks to me like in cosmology, they're at the point where their grandiose general theory of relativity just isn't working to match the observations. So they have to bring in dark matter and dark energy, which look to be ad hoc hypotheses, and to fix a theory that's broken.
Right. And the image of the Leaning Tower of Pisa comes to mind. And the foundation is wrong. And they keep adding more and more nonsense to compensate for the foundation being wrong. And the structure is leaning more and more, and it'll crash via the effect of gravity. Maybe it'll take another 100 years, though.
Oh, I see.
And what do you think when it will happen? Harry?
I think possibly.
I don't know, but I really, I think the requirement that there has to be a better theory is kind of one of those institutional impediments that they deliberately put out there to prevent anybody from making any headway in an alternative theory. It's like you can't get any funding to do research unless you have a better theory, but you can't get a better theory until you have funding to do the research. So that's kind of a vicious circle there. Wanted to mention that I do like the womb theory that Vladimir has proposed, and I think that's really something that's an improvement. He doesn't have all these different parameters in his theory, like the Lambda CDM model has 6 parameters. Womb has I think only 2. I think that's a big improvement. One of the other things is that you have these, and womb is really based on the Dirac heritage. It's a heritage from Dirac, and also some very classic physics, heaviside Dirac. You mentioned Mitchell. I don't see one of the things that kind of bothers me about the rotation curve issue is anybody looked at maybe the gravitational constant is changing, and does that explain why the rotation curves are flat rather than what the theory predicts? Has anybody looked at that? Well, I couldn't find where that was even looked at. So they're not even looking at anything that doesn't mean it. General relativity. It's general relativity. If it's not general relativity and based on the assumptions of general relativity, they're not looking at it.
Well, what I like about Vladimir's theory is that the foundations and basics is empirically driven rather than empirical evidence avoidance by adding dark matter and dark energy, whatever. Or the inflation theory.
Thank you so much, guys, for supporting my model. But unfortunately, it's only in-house models. That's simple. Nobody will accept it.
So, Vladimir, when do you expect to win
that's
the
the
Nobel Prize?
conventionalism issue
Nick, it's very simple. When will you submit this proposal to give me Nobel Prize? That's it, simple like this. I'm joking, of course. It's not Nobel Prize. I don't care about it, because as for me, the last maybe 10, 20 years Nobel Prizes in physics, it's nothing. It shows the crisis in physics. That's it. Take a look what for they have these Nobel Prizes. Even for acceleration of our universe based on supernova 1A and maybe 20, 30 galaxies, that's it. And because of this, we have lambda parameter inside of the equations. And what is important, it's varying in time. And it's only 120 oh my goodness, degrees. It's varying during the time. Orders of magnitude, 120 orders of magnitude varying from the beginning up to the now. Man, the discrepancy, 120. I don't know. Look, it's so. I have no words. Sorry. because I cannot accept it at all. At all. It's totally wrong. Totally wrong from the very beginning. That's it. Simple like this. Even homogeneity and isotropy. In my model, it's an intergalactic medium. It's observed by fast radio bursts. It's homogeneous, it's isotropic. And all the macro objects is anisotropic, inhomogeneous, and all this stuff. It's simple like this. That's why you can use the same equations. Everything's the same if you will be based on intergalactic medium. What is important? Even notions, space, time, gravitation, you can introduce only when you have the medium. Before the medium, you cannot tell anything about it. This is my point. Many times I told you guys. That's why in Big Bang model, there is no definition. What is means space? What is time? Where they came from? All these particles, including dark energy and dark matter. Nothing. How we can accept something based on nothing? At least in my model, universe created matter,
Well-
universe created particles. Let me tell you the difference. The difference, it is invisible. But the very first dark galaxy was observed with some X-rays up to 60 kiloelectron volts. You see, there was no visible light, but there was a Röntgen X-ray of lights. It's not lights, X-rays, beams. It's better to tell. But what is important? It's invisible dark matter, but you have all the different wavelengths after they interact with the standard hour matter, with the standard ordinary matter. X-rays in the dark galaxies. In dark galaxies, we can see 21 centimeter radiation. It is one more time self-interaction of dark matter particles, not dark matter. Universe created. At least I answered the question. Maybe it's not satisfactory, but I told guys, there is a universe, and it's a creator of these universe created matter and particles. And our standard matter is the result. It's a byproduct of their existence. And then, 7.2% of ordinary matter, even plasma cosmology, let me tell you, it's based on 2.4% of our matter in the universe. How it could be valid if you have only 2.4% in your hands, intergalactic plasma. That's it. And they're doing something with plasma, some macro objects and all this stuff. But all the rest stuff, 97.2%, where it is for plasma cosmology. Guys, I'm ready to hear them. I want to ask them these questions. I was in touch with all of them by letters, by my papers, and so on and so on. But they don't want to take it. Conventionalism, you're absolutely right. Different religions, plasma religion, Big Bang model religion, and all this stuff. And Nick, thank you so much for the very right definition, the difference of my model from other models. It's from experiments based on the results, on the observations only. It should be all the time the correlation, even coincidence with what I calculated and what is really observed. Temperature of microwave background radiation, nobody ever calculated. Never. They don't know what they're looking for. I'm very sorry. That's why you're absolutely right. You're absolutely right with understanding of my model. It's from experiments, from observations, from what we have around. And this, dark matter, I don't know what they name it. What is this? They never gave any definition. Dark matter particles, you're looking what for? What for? Tell me, what is your dark matter particle? They're playing some mathematical games with some parameters. By the way, they have 6 main parameters. Every year, they have additional parameters. Martin Lopez Corredora, I know him for 20 years at least, and he told me that they have already more than 20 parameters to fix their problems with Big Bang model. 6, it's only main parameters. Any new experiment immediately changes of all these parameters. And they build theory on variable parameters. They adjust these parameters. What kind of the theory it is? In my case, I have two parameters. They are standard. They don't connect to any observations and all this stuff. No, model must be on some dimensionless parameters only. And they have parameters, they variations of these parameters all the time. Guys, what kind of theory? Based on variable parameters. I don't understand it. And what is about, at least I gave you some idea. Okay. It was, Dirac who told that there is a creation of matter. I gave you creator. Ask him, creator, how he produced this particle. But I know that all these radiations inside of our world, they have some source of it. Why we have 21 centimeter? Why have this? Why we have X-rays and all this stuff? Because there are some variations of our universe-created particles, and they interact with each other and give us X-rays, gamma rays, and all the other rays in our world. You see, at least I could answer myself the question where they came from, this so-named dark matter, and how we can observe them. Indirect, they try to find their direct, measurement of these dark matter particles. It's absolutely right. Suppose that neutron we have. Can we see it? No. We calculated neutron. We calculated the mass of neutron because there is no charge. There is no way to measure this. This is the point. We can measure we can see particles only with electrical charge. But how many of them? 2.4%. And all the rest, what is it? That's why it's invisible matter, but with a different way to produce radiations by self-annihilation of these particles. And then you can see all of them. And what about the heavy elements? We have all the heavy elements on our Earth. Let me ask you the question, how we produce it? We are not supernova. We are not. And nevertheless, we can find all the elements of Mendeleev table on our Mother Earth. We should understand this. We should explain it. That's why we don't need supernova. We have our Earth, and we have all the stuff around us. How? I'm very sorry for my emotions, but thank you so much for good presentation that showed all the story about the Big Bang model. It's a magic story, it's only mathematical, plane equilibrium, all these, equations, Einstein equation, and it's only confidentialism, as you named it. Sorry for my emotions, guys, because I'm tired of them. I mean, of these guys, they're doing their job. They don't do physics for 50 years already. I'm very sorry.
Well, Vlad has gotten down to 2 parameters, and the next step is no parameters, as we have in binary mechanics. That's when you really have something.
Yeah.
Okay,
Because
please
any
give your
parameter-
presentation about your theory, 1 hour, and we will see what is going on with your theory. It's exactly very good proposal right now. Let's talk about some other approaches, some other models, because we don't need special relativity, we don't need general relativity, Big Bang model, all this stuff. All of us, we convinced that there is no value for them. Let's start to talk about some alternative approaches, even plasma approach, plasma cosmology, your cosmology, guys. It's a very good point of our society. We are dissidents, let me remind you. Let's start not only to blame them, but let's propose something from us. You see what the difference is? Because to blame, it's one story, but please give your own theory, your own model, and we will see if it's valid or not. If there is some correlation with your model and observations or not. Simple like this. And it will be a very good, cosmological sessions about different approaches, how to explain our world, where we live with you guys.
I would say it's impossible, as the Big Bang Theory suggests, that the universe is finite in time and space. I think it's inevitable that the universe is infinite in time and space.
In my model, our world is finite. I can calculate even the volume of it and what is the energy density and all this stuff. This is the difference, you know. I don't understand zero. I don't understand infinity. You know, in my model, there is no zero at all. My model starts at 10 to the minus 18 minimum time, and that's it. Before that, we have no idea. We have nothing because we didn't generate our medium. We cannot start talking even about anything, space, time, gravitation, without medium. There is no medium, there is nothing. Simple like this. There is no singularity problem. There is no the beginning of time. There is no, you see. And the same story with infinity. 93 billion years in Big Bang model, light years. And what is important in my model, there is now 93. There is a value, or I can calculate volume, energy density, everything in finite. You go. It's finite. It's not infinity.
If there wasn't a beginning, though, that means that the universe is at least infinite in time.
No, it doesn't.
It doesn't.
No.
I told you, time you can talk about after you have already medium. If there is no medium, there is no time. No time. Forget it.
Time doesn't
No
exist.
space, no time, no gravitation. Even Einstein, he told about this. It was his insight. I cite him many times. Without matter, there is no way to talk about all this stuff. But he claimed it already. On my model, I showed you guys. It's not claim. I showed based on my model where and when we have our space, time, and gravitation. And gravitation, it's a classical phenomenon. Forget about gravitation between particles. Look, it's bullshit. I'm so sorry. We have no gravitational connections between particles, our standard one, and suddenly we are trying to demand, to request from them to have a gravitational force. Come on, guys. It's not fair for universe created matter. Universe created matter you can watch in all other not wavelengths, in all other energies, in all our other beams and all this stuff. It's not visible. It's not produced by electrons. It's produced by nuclear reaction of self-annihilation. There are no electrons. Electron will be as a result of this self-annihilation. This is very important to understand that visible spectrum and all this stuff, what we can see, it's only based on electrons.
Okay, we're coming up.
Okay, sorry for my too many words.
Okay, we're coming up on the end here. I got 5 minutes. Anybody got any quick comments before I try to wrap this up?
I'd like to, correct one point. General relativity or the gravitational field equations do not predict the uniformity of everything being exactly the same, because gravity inherently will cause structures to grow. But as Harry articulated in detail, some of these huge structures just are not explainable by or consistent with the cosmological principle of everything being purely the same. And that's why Smoot won the Nobel Prize, because of his finding the whispers in time. But if you go into the details, they were looking for evidence at, and I don't remember the exact numbers, but 1 part in 100. Didn't find any. So they went to 1 part in 1,000, didn't find any. So they went to 1 part in 10,000, didn't find any. They went to 1 part in 100,000. They found this signal, but they had, tremendous amount of data, and the software was getting rid of everything that didn't match the signal. So at some level, they were bound to find it, which is exactly the point that Professor Unziker made about their alleged finding of the Higgs boson. If you have tons of data and you have filters to filter out everything that doesn't match, you'll eventually find what you're supposed to find, and then the champagne gets popped and you win the Nobel Prize. So, or conventionalism.
Yes. Okay, so that leads into my into my thesis, which is that if you propose something that doesn't fit into the physics that they're teaching, you get ignored, and so that forces everybody to march to the same drummer. And I think that Vladimir has made a point about the medium, and I'm kind of an Einstein guy. I mean, I'm sorry, Aristotle guy. So I'm going to say Aristotle had this idea of quintessence, which is the substance of the heavens or the universe around the earth. And I think we're still trying to, determine what that is. And I think what Vladimir is saying is that we need some kind of a medium, that the universe has to have some substance. Aristotle would have used the word substance. He would have said the quintessence is a substance. And in my view, general relativity is really a theory about the metric, and the metric is space, which is nothing. And so in the end, physics just becomes a theory about space, which is nothing, and time, which is indefinable and indescribable. So what is physics ultimately about? What is the universe ultimately? What is it? And physics seems to be relying on these ideas that it's just philosophical entities which are really non-existent. So it's not physics anymore, it's just mathematics. So That's my objection to what physicists are doing. They're just doing mathematics and not really physics. Okay, somebody wanted to, we're almost at the end. I did want to mention that we're going to have a meeting tomorrow morning at 10 in the Cosmology discussion group. If you have any comments about what we've talked about here, suggestions or anything, email me, kc3mx@yahoo.com. Again, kc3mx@yahoo.com. If you're not on the distribution list or the announcement list, I noticed that Jerry apparently wasn't on the distribution list. I guess you can send me an email and I'll relay that along to David DeHilsky. Okay, I want to thank everybody. Have a good Saturday.
Thank you, Harry.
Yes.
Thank you, Harry.
Congratulations for the beginning of our cosmological session.
Okay, I'm hearing static. Okay, I had a problem because I couldn't really, my computer was getting all screwed up with buffering. So I'm not sure exactly what that was caused by.
Yeah, that buffering is a problem. StreamYard, I think this CNPS should switch to Zoom. I participated in meetings where 70 or more people are involved, and the host of those meetings can control who can speak in terms of muting their mics or unmuting them, as the case might be. So I really think CNPS needs to move.
All right, well, let me ask you this, Jim. Did you have...
Go ahead.
Did you have buffering issues? Huh?
Well, today,
did
for
you have
example,
buffering issues, Jim?
Well, if if by buffering you mean those little circles where the screen goes black and little circles
Correct.
up here, is that what you mean, Harry, by buffering?
Yes.
Well, yeah,
Yes.
today I saw buffering
Yes.
several times, and then you cannot hear because the screen goes blank, and you have those little circles like indicating it's loading the image, and so we black out. In the Zoom meetings that I participated in with maybe 40, 50, or even more participants, I've never seen that kind of buffering. Never. I don't know why
I
we're
know.
using StreamYard. Go ahead, Harry.
Yes, well, I had quite a bit of it. In the beginning, it was fine, no problems, but then after a while, it just became annoying, and I couldn't hear what people were saying because it was just becoming a problem. And I don't know whether it's me or what. My computer, but I agree with you, Jim. I've never had any problems like that on Zoom.
We really should. I bet
All
you the
right.
Zoom is cheaper than the StreamYard for CNPS.
I don't know what the deal is, and I don't. I don't know. The idea is with StreamYard is that it connects to Facebook and YouTube at the same time, and I don't know. I think that's the whole point of using StreamYard. At least
Well, you
that's
don't
my
really need
understanding
to
of it.
connect
So
to.
I
What if all those people on Facebook and YouTube could actually just join the Zoom conversation? Have we ever had 30 or 40 people and in Facebook and YouTube combined? I doubt it. Zoom can handle that easily so that everybody can be live. And again, the host can determine whose mic is muted or not, as the case might be. And so you have then the coverage, and then also you can record the one group that I participate in. They record the sessions and put it on YouTube afterwards. But this connection, this live connection with YouTube and Facebook is not necessary if everybody there could just come and participate in the meeting. So we don't have to be the host doesn't have to be looking down and saying, what are the comments on Yahoo, or excuse me, on YouTube, to address to our speaker and so forth and so on.
Would they have a chat room?
Yes. In the Zoom, you has the capability of entering chat items for that everyone will see, or directed only to a particular person. So, for example, if in Zoom, while the Zoom meeting is going on, if I wanted to direct a comment to Jerry only, I could do that in the Zoom platform. Can't do that here in StreamYard.
Would it be live to you?
okay. Well,
Yeah,
we all know that there's problems.
It's no
I've known
need to
there's
have it
problems with
live to
StreamYard for a long
YouTube.
time.
It's no need to have it live to
okay.
YouTube, Jerry, because all the YouTube participants could just come and participate in the Zoom meeting. They would come directly so that there'd be one group of people, everybody included, those who were using YouTube or Facebook to participate blindly, so to speak. In other words, they couldn't say anything except make a comment, written comment.
I don't know if people who might
Zoom
just
meetings,
casually tune in might not show up. People who just casually tune in on Saturdays might possibly wouldn't show up.
When I watch the CNPS presentations, I use YouTube. I don't get on the computer. I use YouTube. It's a lot easier to do it with my TV set, and the TV set has a bigger screen than my computer. Anyway, thanks everybody
cool.
for coming.
Thank you, Harry. Thanks,
We'll
everyone.
talk to you tomorrow morning.
Okay, see you tomorrow.
Okay, do you want to end session now? End stream. End stream, Harry. Harry,
Yes, what?
that you can click on end stream now on the top right. Shall I click on end stream? End the session, end stream.
I did. I clicked on it, but I'm suddenly in. It's giving me some
Giving
kind of
you
an
live
error
still.
message. All right.